this is a very, very different unit than the last one. In this one, it's all about, we're going to do reasoning, okay? And there's different types of reasoning, and there's different vocabulary that we need to know. And you know that stuff that we've been doing on the sideboards, doing problems, right? That is what reasoning is, okay? So we look at patterns and see what's going to happen next, which is a mathematical concept. People don't realize that, like if you were about to get in a lineup at Canadian Tire, and there's 6 lineups, many people do math before they get in those lineups. And I'm not talking about adding stuff together. They look strategically on which line to get in. And they look at, okay, if there's a little old lady in there that's like got a bunch of change that she's going to be counting out, maybe stay away from that one. And what if there's people that all have 2 items, and then you see that lineup, people have a bunch of carts full of stuff, stay away from that one. That's mathematical reasoning. That's not something that comes into any other course. Okay? It's logic. It's thinking before you, and have you ever just got in any lineup and then you look at the other one just moving and you're like, I didn't even think about this. Like, it was stupid. Why did I get in this lineup? This one's full of people that have huge carts, and there's probably going to be 3 price checks, and you know, and look at that line moving. All those people just had a few things, okay? And that's when you learn to get a little smarter and get into the right lines versus a right line versus not at all, right? So today we're going to be learning about 3 things: inductive reasoning, conjectures, and counterexamples. Okay? And you would be surprised how many of you know these already, but you maybe didn't know that was the word for it. Now, let's just look at this. This is a diameter, cuts your circle in half. And do you know that on your diameter, if any time you take, so from A to B, you go one place, over, and then back, it will always make a 90-degree angle. So what does that mean? That means, okay, so I should be able to go like this then. Hit this side, and then down here. And believe it or not, it does make a 90-degree angle. You could do it over and over again. Get your protractor out, and you will find every single time. And then you could come down here and do this one. You could try this one. And believe it or not, every single time will make a 90-degree angle. So the question or the conclusion you can make is that any angle made on the circumference of a circle whose arms, I'm sure you wouldn't think to do it this way, but whose arms pass through the endpoints of its diameter is always 90 degrees. Okay, now you want to try it a crap load of times to make sure it works. Not just one time. Okay, not maybe even 10 times. Maybe you got to do it many times to see if it fails. Until you can say, you know what? That's true all the time. Okay, Now, Bruno's investigating his fabric design for new furniture he's making. The original design is based on a trapezoid. His first two complete sketches and the third incomplete sketch are shown. Okay, so here's a trapezoid. So in sketch 1, all he did was add 2 new trapezoids, 1, 2. And in the second sketch, he added trapezoids. If you can see, he added trapezoids to each one of these two to get 1, 2, 3, 4. So in sketch 2, there was 4. Now in sketch 3, right, he's going to add trapezoids to every corner. And how many are there? How many new trapezoids did we get? We're just looking for the new ones. How many new ones? Count them up. 1, 2, 3, 4, 6, 7, 8. Now, it's a lot of work drawing all those trapezoids, and look how bad mine suck on top of that. So they're even ugly trapezoids. Is there a better way? How many do you think would be in the fourth? 16. How'd you get that? See how it's been doubling? So at 5, there should be 32, and at 6, there would be 64. There's even a better way to do it, because what if I wanted the 20th? Then you're like, that sucks. I got a blah, times 2, times 2, times 2, but there's a better way. What is a way you could use these numbers to get these numbers? Like, what can you do to 2 to get 4? Or how could this? Okay, so I'm going to show you a little trick. This is like 2 to the 1. This is 2 to the 2. This is 2 to the 3. This is 2 to the 4. This is 2 to the 5. This is 2 to the 6. So to find the 20th, I would do 2 to the 20th. So, because it keeps doubling, right? So you got 2, and the next one's 2 times 2. The next one's 2 times 2 times 2. The next one's 2 times 2 times 2 times 2. So that's how you get 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, right? So, what conclusion can you draw for the 10th sketch? The number of trapezoids should be 2 to the 10, or 1024. Okay, so believe it or not, what we've been using is called inductive reasoning. Now, what is inductive reasoning? Okay, inductive reasoning, let's just read along right here, is a type of reasoning in which we arrive at a conclusion, generalization, or educated guess based on experience, observations, or patterns. So it's based on experience, observations, or patterns. The conclusions are called conjectures. We're not going to use the word conclusion anymore. So, a Conjecture is when you make a decision arrived at by inductive reasoning. Now, inductive reasoning means that last Sunday you went to this little store on the corner and it was closed. Okay? The next Sunday you went to that store and it was closed. And then someone says to you, yeah, I'm going to go to that little store on Sunday. You go, it'll probably be closed. That's inductive reasoning. Now, it may not always be true. Maybe for those 2 Sundays, that person was away. And maybe they're back and now it's going to be open Sunday. Or you walk into a computer lab. And the first computer's a Mac, and the second computer's a Mac, and the third computer's a Mac, and you go, this must be a Mac lab. It's all full of Apple. But maybe there is some PCs in there, right? Or you lend your buddy money, he doesn't pay you back. He asks you for more money, you lend it to him, he doesn't pay it back. The third time he asks to borrow money, you say no. Why? You're using inductive reasoning. Now, is it for sure true he won't pay you back? Is it a guarantee? Would you bet your life on it? No. But we use inductive reasoning all the time. You just have to realize that it may be false. Okay? Like, you know, the last time I had a math test, I had chicken that night, the night before. And I did awesome. And then the next time I had a math test, I had chicken that night. And I did awesome. So from now on, I'm having chicken before I write a math test. And sometimes people do that. Superstitions are based on that a lot. Like hockey players, a lot of them have superstitions. That they always have to put on the right pad first, or they always have to be putting on the left skate first. Always. And they'll find out the times they don't, they play crappy. So by inductive reasoning, they say, if you don't put your left skate on first, you will have a crappy hockey game. So is all inductive reasoning based on fact? No. Many superstitions are based on history of inductive reasoning. You know, there is diseases, you know how diseases are contracted. You know, we got to make sure we wash our hands. You know, that's all based on inductive reasoning. They found that if you wash your hands, that the flu is not spread as wide. Okay? Now, just remember that that conclusion or generalization is called a conjecture. Now, I got to ask you a question here. If your parents say, you know what, I'm sick and tired of you in this house, you never ever clean up around here, and it makes me mad. How have you, what would be something you could say to that that could stop that conjecture? You could clean, yeah. That wouldn't stop the conjecture. You would actually keep that true. You could clean, or you could say, I cleaned up the house last Tuesday. Okay? And if that's true, of course you have now disproved the conjecture 100%. That's all you need to do. In life and in inductive reasoning or conjectures, you just have to give one example of where that is not true, and it throws it out. Same with the court of law. Okay? If you can just give one example where that is not true, then it's considered never true. Okay? So if your parents say, you know what, I'm sick and tired of you're just here all the time. You don't do any work. All you do is freeload this, and you're like, but I like cleaned up the whole house last week. That means then that's not true. If that was a court of law, the judge would say, well, is that true, Mom? Did she clean up? Yeah, she did. Okay, well then this case is over. You can't make that statement. It's not true. And if your buddy's like, and you're like, I'm not lending you any more money because you never pay me back. He's like, I paid you back like last week. Right? You may not lend him the money, but that's not true. If that was in a court of law, you would lose. Okay? If you can prove that that statement is false by one counterexample, then it is false. Okay? And we're going to talk about that in a bit too. So this is super important, you guys. Conjectures may or may not be true. In fact, some are complete lies. A lot of sometimes people just get these ideas in their heads because maybe their parents told them that, right? Anytime there's racism or things like that, people get stuff put in their head that's not even true, but they just believe it to be true and they act off it. Okay, that's what racism is. Discrimination, right? People discriminate against another culture, right? Because, oh, they're not as good as us. Well, where did you learn that? I was taught that, and I believe it to be true, right? And the only way to disprove that is to show many, many, many examples of how that race or that culture, that's not true. And that's the only way we get rid of that racism and discrimination. Okay? Now, because we kind of already did that. Now we're going to talk about counterexamples. Now this is super important. If a conjecture will be true unless you can provide one counterexample. You don't have to do 10. It's just one. And it proves it to be not true. So a counterexample shows the conjecture is not true, aka false. Okay? So I want you to look at this one. Katie and Perry. It's kind of funny that they use those two names. I wonder if it was a coincidence. I don't know. Were given the following number pattern by their teachers. Katie's task was to make a conclusion based on only the number of patterns shown and no further investigation. So she found that from this 2 squared plus 1 equals 5, 4 squared plus 1 equals 17, 6 squared plus 1 equals 37, 10 squared plus is 101, 20 squared plus 1 is 401, and 36 squared plus 1 equals 297. Now if you look at all these, they're all prime numbers. Now what's a prime number? Anyone know? Math 10? Right. It can only be divided by 1 and itself. So like 6, well 6 would be 1, all of the factors would be 1, 2, 3, and 6. So 2 times 3 is 6, right? But if I gave you 5, what times what equals 5? Well, only 1 and 5. So it can only be divided by 1 and itself. So 1 times 5 is 5, that's it. 12, I can go 1 times 12, I can go 2 times 6, I can go 3 times 4, right? That has more than 1. So she had to provide a conjecture based on this. She's not asked to come up with a counter if it's true or not, but her conjecture, when an even number is squared and 1 is added, the result is a prime number. So Katie's conclusion is a conjecture based on inductive reasoning. Now, what's her conclusion? When an even number is squared and 1 is added, it'll give me a prime number. Is this true? You can't say no unless you can give me a counterexample. What's that? No, all of these are prime numbers. Every one of these is correct and true. Is there, can you give me an even number squared and 1 is added, and the result is not a prime number? Because if you can't, then this remains true. And that's what every single lawyer does. Finds something to disprove, especially any defense client. Anybody that is been charged with something gets a defense lawyer. And your defense lawyer is very good at finding one counterexample. If they find that one counterexample, they get you off 100%. So 18 squared. Okay, let's go with the smaller one, 18 squared. 8 squared plus 1. That's 64 plus 1 is 65. Is 65 a prime number? No, this is called a composite number. Because it's more than 1 in itself. Because 65 divides by 5, right? If I do 65 divided by 5, it's 13. So you can divide by other things than just 1 in itself, right? So this proves that this conjecture is false. Therefore, Katie's conjecture is false. So, if someone tells you every person that works for us is completely honest, okay? And if you catch one person stealing, you get to say back, well, there you go. I just disproved your conjecture. Every person working for us is not honest. We need to be watching. Okay? If, you know, some neighbor's complaining that your dog always crops on their lawn, and you're like, my dog has never ever cropped on your lawn. Meanwhile, you look down and the dog's cropping on the lawn. I think you kind of look like a fool at that point. And it looks like he's done it all the time, right? And that's the bad thing about ever making a conjecture that is false, is that you feel like an absolute fool when somebody proves you wrong. Okay? And that's why parents don't like that. When they say that you're a pig, you never clean up, you just expect everybody, and you give them an example, do they go, oh, that's a really nice example. Thanks for that. I am very calm now and cool, collected, and I am sorry for everything. Right? Never goes that way, does it? So there's times that we don't even point out the counterexample, because it's like, okay, fine, yep, I'll just clean up. Because you provide that counterexample, and you get in more trouble. You're talking back, or you're whatever. And that's why it's, I guess, great to be a lawyer, because you get paid for talking back, right? Now, let's try another one. Now, this, when a conjecture is false, it may be possible to revise the conjecture. Okay? Because sometimes you can. Because maybe your parents will say, because you'll just like, oh no, you remember last year on September 16th, I picked up my coat? Yeah? Yeah. And then your parents go, no, in the last year, you have not done anything. And then you're like, oh, I'm screwed. Why did they make it, right? They said never. I liked it when they said never. I've never helped clean up. But now they said in the last year. So they revised their conjecture, and now you're screwed, right? Now, what are you thinking right away? Come on, come up with something. Come up with something that I cleaned in the last year. Get it now, right? And then maybe you can't. And then later you're like thinking about it. Oh yeah, there was that time I should have said that. I wish I would have said that, right? Now, so Mick and Sue were discussing what conjecture could be made following with regarding these following prime numbers. 3 plus 5, so these are all prime. 3 plus 5 is 8. 5 plus 7 is 12. 7 plus 11 is 18. 13 plus 17 is 30. 19 plus 23 equals 42. And 29 plus 31 is 60. So they both agreed this is the conjecture that they're going to make. The sum of two prime numbers is always an even number. True or false? And don't say false unless you can tell me why. And that's why people who cannot find counterexamples, they fall for everything. Have I got a deal for you? It will not fail. Right? And you're not willing to like do some research and find out actually it fails a lot. I'm not going to go into business with you. And that's mathematical reasoning. You only learn that in math, right? It's coming up with something to say, nah, no, I'm good, right? But if you're not good enough at finding a counterexample, then basically you have to do whatever happens, right? Anybody got anything? So is this true? There's only one counterexample that fails. 2. 2 is a prime number. And look at 2 plus 3 equals 5. There. That is not an even number. Therefore, that conjecture is false. So the question is, could you revise this so it holds true? Right. So the sum of two prime numbers, you could put the sum of two prime numbers, well, maybe I'll use the word TWO, two prime numbers, except for 2, or we could say excluding 2, is an even number. Okay? Now, make a conjecture based on the number pattern in these conditions if they took away prime number. So if we got rid of prime number, what could we say that has happened here? What are all of these numbers? Odds, right? So we would say the sum of two odd numbers is an even number. And that's my favorite thing about the whiteboards, when two people are working together and somebody comes up with something and someone goes, wait a minute, That's not true. Here's why. And they say why. When they're in that why territory, that means they get what's going on. Okay? Now, Jerome investigated the following number pattern. 1 plus 2 plus 3 equals 6. 5 plus 6 plus 7 equals 18. And then negative 6 and negative 5, negative 15, negative 12, negative 11, negative 10 equals negative 33. He noticed that in all the patterns, when three consecutive integers were added, when write two more number patterns showing the sum of three consecutive integers. This one's pretty cool. So when you have three consecutive numbers, what's a faster way to find the answer? Like 21 plus 22 plus 23. What does that equal? 66. Now, what happens? I just want you to look. What happens if you take the 1 away from here and add it to here? We get 66, don't we? So isn't this like, because if I bring it over here, since this is always one less and this is always one more, I can bring that here, right? And what would I get? 3 22s. 66. So if I just gave you this, so I want you to just watch quick. If I gave you 99, 100, 101, what would be the sum? 300. What's a fast way to do it now? The middle number times 3. Look, 2 times 3, 6 times 3, negative 5 times 3, negative 11 times 3, 22 times 3, 100 times 3. Right? Because that 1's always going to come here, and that would be 100 plus 100 plus 100. Right? So, use inductive reasoning to make a conjecture. The sum of 3 consecutive. Now, consecutive means one after the other. January, February, March. Consecutive integers is equal to 3 times the middle integer. Now, can you give me an example where this would not be true? This one's pretty hard. You're not going to find one that... So there's no counterexample, therefore it will be true. Now, we're going to learn how to prove it using logical or deductive reasoning next. Okay, so now what we want to do is let's get out our blank piece of paper. And we're going to write down what we learned today. So, because your quiz is going to be far away. So then you could just pull that out and get it all back, okay? And I want us to be updating our study sheet every day. So at the end, we've got our study sheet done, okay? So this one, we are going to title it Mathematical Reasoning. No, we're going to keep that. We want to keep our sheets separate. Okay, so lesson 1. And then we don't have to do this at the end. We're going to know it. Okay? Now, if we go back to the first page, what did we really learn there? We just did a bunch of stuff, right, that we just got going. So let's get our definition for inductive reasoning. Right? Because if we have this, then the next time we do deductive reasoning, we can look at them at the same time. So it is a conclusion generalization or educated guess based on experience, observations, or patterns. Okay, so then let's get a conjecture okay, that is a conclusion from inductive reasoning. Okay, and then the last thing, a counterexample is an example which shows a conjecture is false. And remember, it takes just one. Don't have to provide 20. Sometimes we want to provide 20 because it makes us sound better and we want to keep yelling and we want to, and I did it on Wednesday and then I did this and I did this, right? But in the court of law, it's just one. One counterexample, and then that conjecture is no longer true. Okay? Cool. So what are we working on? We're going to work on 1, 2A, 3, 4, 5, 6, 7, 8A, and 10. Writing